Let's talk about photon momentum now. We said that light has a dual nature, right? We said that in some instances, the behavior of light is best described, is best interpreted in terms of a wave. And in some cases, its behavior is best interpreted in terms of it being made up of particles called photons. Now, the energy of each photon, we said, is going to be equal to h nu. And from relativity, the energy of any particle, according to relativity, the square of the energy is equal to p squared c squared plus m squared c to the fourth, where this p right here is the momentum, okay? Linear momentum. And in classical mechanics, Newtonian mechanics, based on Newton's laws, momentum is defined as just mass times speed, okay? And that's what you learn in your introductory physics classes, right? Momentum is mass times speed. But if you apply relativity, momentum is mv over 1 minus v squared over... Let me rewrite this to make it easier to read. This is actually this is m naught. It's called the rest mass, the mass when the particle's not moving, okay? Times v over square root of 1 minus v squared over c squared. Okay, so this term right here in the denominator. That's the relativistic formula for linear momentum. Okay? Now, since a photon is a massless particle, m naught for photon is 0, okay? Then it would seem that the momentum of photon should be 0, right? But since it is found to demonstrate momentum, okay, when it interacts with small particles, it is found to have momentum. Okay, the way you can justify having a momentum for a photon is when you apply relativity. Well, if you're approaching the speed of, when you're at the speed of light, what happens to your denominator here? When v is equal to c, what happens to this term right here? 1. And what is 1 minus 1? 0. So that becomes 0 over 0. So that sort of justifies giving a particle with a massless particle having a momentum, because 0 over 0 doesn't mean it's going to be equal to 0. Okay? So if you have a massless particle, then you'll say that this term will drop out, right? 0 mass. Then you can say that E squared equals P squared times C squared, so that is E equal to PC. What that suggests then is that the momentum of a massless particle has to be moving at the speed of light. So C is the speed of light. So the momentum of a massless particle is E over C. Okay? Or since a photon has an energy equal to h nu, that's going to be equal to h nu over c. So the momentum is h nu over c. This is another way of looking at it. Energy is pc. It's also equal to h nu. So you solve for p. The momentum of your photon is h nu over c. But what is nu over c? Remember, lambda nu is equal to c. So what's nu divided by c? 1 over lambda. So that's just h over lambda. So what does this thing say? The momentum of a photon is inversely proportional to its wavelength. The longer the wavelength, the smaller the momentum. The shorter the wavelength, the higher the momentum. So which photon has greater momentum, an X-ray or an infrared photon? X-ray has more momentum. Why? Lambda for the X-ray is less than the lambda for an infrared photon. So your X-ray would have more momentum. Okay, so stationary hydrogen, here's an example here. And a stationary hydrogen atom releases a photon with wavelength of 122 nanometers. Calculate the recoil velocity of the atom. So imagine you have a hydrogen atom here. It produces a photon with 122 nanometers. So if the photon is, okay, is released and it comes up to the left, what would happen to your atom? It's going to recoil in the opposite direction, law of conservation of momentum, right? So whatever the momentum of the photon is, that's going to be the increase in the momentum of your atom. And since your initial momentum of the atom is 0, it's a stationary atom to begin with, then whatever the change is, that would be the final momentum. So how are we going to do this? Okay, what's the momentum of the photon? H over lambda. Yes. Momentum of the photon is h over lambda. 6.626 times 10 to the negative 34 joules second. What's the wavelength of the photon? 122 times 10 to the negative 9 meters, and that gives us 6.626 times 10 to the negative 34 divided by 122 times 10 to the negative 9 equals 5.43 times 10 to the negative 27. 5.431. Okay. Three sig figs here. So 3 is the last digit there. That's sig fig. And what's the unit for momentum? Mass, unit of mass, which is kilogram, times unit of speed, which is meter per second, right? Is that what you get from joule seconds over meters? What's a joule? Kilogram meter squared per second squared, right? That's seconds divided by meters. So what does that give you? Yes, units of momentum. Meter squared over meters is just meters, right? And per second and second just gives you per second. So that's your unit for momentum. That would be the momentum of the hydrogen atom. So if the hydrogen atom releases 122 nanometers, it's going to recoil with that velocity, with that momentum. So what's the velocity of the photon, of the hydrogen atom? You can just say P equals mv. So what's the velocity of your photon? I mean your hydrogen atom. So it's going to be equal to P over m, which is 5.431 times 10 to the negative 27 kilogram meter per second divided by, what's the mass of a proton? Mass of a hydrogen atom. Mass of a hydrogen atom is 1.67 times 10 to the negative 27 kilograms. You remember how to figure that out if you haven't memorized that number? 1.008 grams per mole, right? And then you change it to, 1 kilogram is 1,000 grams, right? And 1 mole is how many atoms? 6.02 times 10 to the 23rd atoms. Okay, so that gives you the mass for each atom. Think of it this way. 6.02 times 10 to the 23rd grams is equivalent, 6.02 times 10 to the 23rd AMU, atomic mass units, is 1 gram. You can use that as a conversion. Okay. A mole of AMUs is 1 gram. Okay. So that is the correct number? Yes. You sure? Let's verify. Let me just verify. 1.008 divided by 1,000 divided by 6.02 times 10 to the 23rd Yeah, 1.67 times 10 to the negative 27. Okay, so it's the mass of one hydrogen atom. So 1.67 times 10 to the negative 27 kilograms. So kilograms cancels out, and that gives you how much? 5.431 times 10 to the negative 27 divided by, oh, you could have, you need the 10 to the negative 27, right? That will just cancel out, makes it easier. Okay, so 5.431 divided by 1.67, that gives you 3.25 meters per second. Okay. Now that's kind of a slow speed, so that's within the realm of classical mechanics. It's non-relativistic. Remember we said once you're approaching speed of light, you have to start applying relativistic formulas, but this one should be okay, 3.25 meters per second. Okay, so that's how fast the hydrogen atom will end up moving to the right if it releases that photon to the left.